Hello, everyone. It's really my pleasure to be here for this presentation. I'm very excited to be here to present you what we have been doing in Zama recently. So let me share my screen. So I'm going to present ConcreteML, which is our new release, which is for the the privacy preserving machine learning stuff. So I will explain how it works and the different research problems that we are facing. But just to start, so as you have heard, I'm not the usual speaker that you may have in this seminar. So first, because I'm from France, so from the other side of the country, the planet, it's amazing that we can do such a thing with the modern tools. And second, it's because I'm not a typical machine learning person. I am more of a cryptographer. As you, I will speak a bit about Zama. So in Zama, it's a lot of people about cryptography. But just to reassure everyone, I'm going to speak about machine learning. I'm the team lead of a machine learning team in Zama. And I'm going to introduce you this product that we are making. Okay, so so what are we going to speak about? Let's take this advertisement from Apple. So what happens on your iPhone stays on your iPhone. So what does it mean? What does it mean? Sure, the main reason of this advertisement is for Apple to ask you to, let's say, buy their phone. But okay, that's one point. But if we want to go further, it means that on your device, would it be a phone, a computer? There are plenty of data. There are plenty of data which are personal to you and that you don't want to give to anyone. But at the same time, machine learning is running the world, and with those algorithms, you can build plenty of services. So the goal of what we are doing of a privacy preserving machine learning is to protect your data, but at the same time still be able to run this machine learning algorithm, which needs more or less an access to your data. So in the case of Apple, what they say is that because of the privacy problems, they restrict their models to just run locally on the device, which is obviously a problem. Because the models that you can run on a device, on a small device, is are much more are much smaller than the models that you could run on a server. And also you can't update the model as regularly as you could on a server. So that's a way to run machine learning models. The other way is the opposite. Let's say, so for example, you take Facebook. So here they run everything directly on the server. So there is no privacy at all. And at the end, you have a lot of scandals like the Cambridge Analytica problem and at the end, the users do not trust those companies anymore. So now there is this big trend of being able to have the machine learning algorithm running on servers without letting them access to your data, which at the end is great for the users, but also for the companies. Because for example, if ever you have security breaches on your servers, if the data are encrypted, it's no more a problem. You don't need anymore the servers to be secure or trusted. Whatever happens, it's encrypted, so no problem. Same thing, you know, in Europe, there is what is called the GDPR, which are laws to make that the data can't be accessed too much, thanks to encryption. It's yet another way to deal with this law. Okay. So to deal with privacy in Zama, we are building this. We are building on top of a new cryptographic tool, which is called fully homomorphic encryption, which is really a magical tool, which has been, let's say, the cryptographers were looking for this tool for a long time ago, but it has just been a few years ago that the tool has really been, found. I mean that there is not a theoretical but a practical solution that can be done. So what's FHE? So FHE is a very simple principle. So you are on your device where you have a secret key. So each time you want to run something outside on a server, so what you do is you encrypt your data, and then you send this encrypted data to outside. You don't need anymore to trust this outside world, and then to perform the computation of their function, they just apply the function on encrypted data without knowing the private key, without decrypting stuff. So they can do whatever they want, but everything is encrypted, so they don't know anything about the actual value. And at the end of the process, when everything is done, they can just send you the result, which is encrypted as well. And finally, on your local device with your private key, you can recover the result. So if you look on the right of the slide, you can see mathematically how it works. So you have your data X. You have generated an encryption and decryption key SK. So you encrypt X on your device, and then you send it to the server, and then the server is able to perform the evaluation of the circuit F directly on the encrypted values with just public stuff. At the end of the computation, it has computed the encryption of f of x, which is sent back to the client, which with the secret key SK can decrypt it and finally get f of x. Of course, if ever you have questions during the presentation, the slides, I've told you, you can ask on the chat, or you can interrupt me. So that's FHE. It has been really the community, the cryptographic community has looked for it for years. And that's only recently, like 10 or 15 years ago, that finally it has been found. So why the name fully homomorphic encryption maybe? So it's because of the morphism. So just to remind you, morphism is when you have a black circle operation, and there is a relation between f of A black circle B and f of A, f of B. So thanks to that, you can perform operations directly on encrypted values without decrypting. So if you imagine that f is your encryption, and for example, a black circle is plus, you could see that the encryption of A plus B is actually something related to the encryption of A and encryption of B. So if you have just the encryption of A and the encryption of B, you can combine them with the white circle operation. You can combine them to finally get the encryption of A plus B without knowing the secret key. So that's morphism, and it was known for years how to build a cryptographic scheme with a single morphism, so with a single black circle operation. We were able, for example, to do encryption schemes with additive properties. And notably, one of them is the Paillet scheme, which is very famous and which has been used for vote protocols, for example. And Pascal Paillet is actually one of our funders. So it was easy for single operation, but when we want to have several operations, so for example plus and multiply, it's much more complicated, and it's what is called fully homomorphic encryption. So for years I told you it has been thought that it was very complicated or even impossible, but now we know how to do that. And the application to machine learning are numerous. So if you look to machine learning algorithm, you can see that there is more or less two kinds of operations. So the linear operations, like I don't know, the matrix multiplication. So if you have a matrix multiplication, what it means, since it's linear, you can directly use the homomorphic property of the encryption scheme to make that when you have encrypted values, you can very easily, thanks to the morphism equations, compute the matrix multiplication of this ciphertext without knowing the keys. And then the second kind of operation in machine learning is nonlinear operations. So for example, the activation, so will it be a ReLU, a sigmoid, or anything you want? And then, of course, you can't apply the morphism property. So you have to have a replacement for that. So I will explain you a bit more what we do in Zama for that. But there is a way to also compute non-linear operation. Okay, so don't be afraid. It's going to be the only crypto slide of the presentation. So it's if you don't get it or if you don't remind it, it's not a big deal. But it's just to give you an overview of how it works under the hood. So there are several, FHE schemes which are available, several, maybe 3 or 4. And Zama is using one of them, which is called the TFHE. So FHE on the T is for torus. So torus is a fancy name, but actually it just means the floats modulo 1. So just a floats modulo 1. The scheme is based on AWE problem, which stands for learning with error. I'm going to explain a bit why it's learning with error problem. So when you want to encrypt a message, M0 or M, which is just a single bit, what you start to do is you start to encode your message, your bit message on the torus. So if the message is 0, you encode it as 0, and if the message is 1, you encode it on the other side of the torus, which is 1/2. And then to encrypt, you generate n random values, so the AI, which are called the mask, so just random values. And finally, you have the last part of the encrypted value, which is the dot product of the AI with SI, which is your secret key, you remember the SK of the previous slides. So you compute this dot product, you add the message you want to encrypt. So would it be 0 or 1/2? And you add a small error, which is a value which is very small as compared to 0 or 1/2, but which is to make that the last part of the encrypted message, which we call the body, is not exactly the dot product plus a message. So here it's the encryption, and as we are on the torus, we reduce everything modulo 1. So the bracket 1 is means modulo 1. And then when you want to decrypt some message, so with the mask AI and the body B, you just you just have to compute the dot product of AI with SI, your private key. You then do B minus this dot product, you reduce modulo 1, and then either you have something which is very close to 0, which means that the message is 0, was 0, and if ever this result is very close to 1/2, the message was 1. So here you can see that the encryption is pretty simple. I'm not going to explain you why it's secure or some more deeper crypto problems, but just to explain you LWE, learning with error. Why is it this? It's because more or less when you have a lot of encryptions of messages, you learn a lot of dot products related to mask that you know the AI, and a secret key that you want to learn. So you are trying to learn from this dot product, which are a bit protected by the the epsilon, the small error. You are trying to learn what is the secret key, what is the SI. So hence the name learning with error. And then why is that a fully homomorphic encryption? So first you can see, or you can admit that the encryption of A and the encryption of B is an encryption of A plus B. So it's pretty simple. Normally you see that the mask part, the AI part, when you take the AI of the encryption of A and the AI of the encryption of B, and you add them, you get the AI of the encryption of A plus B. And for the body part, the B part, you can see that the dot product, same thing. They add the message. They add modulo 1. So if you, for example, if you encrypt a message M and a message M prime, or A and B, as in the slides, you will get the encryption of A plus B modulo 2. So the bits are, it's a modulo 2. So the linear part is easy. For the non-linear part, it's much more complicated, and I'm not going to detail this, but it's related. So there is a way to compute T of to compute from the encryption of A, the encryption of T of A, where T is a table that you can choose. So it's what is called the programmable bootstrapping, which is one of the core techno of the Zama company. And it's really important because it's the only way for us to compute nonlinear operations. The bad part of this is that it's pretty slow. So you will see, but when we turn machine learning algorithm into their FHE equivalent, we try to avoid to have too many programmable bootstrapping PBS. Same thing if you have questions about the crypto. I told you it's the only slide about crypto or normally. So if you want to ask them, it's now or at the end of the talk. Okay. So now that we have explained a bit the premises, let's say, let's speak about the product and what we can do with it. So concrete ML, it's something that we have released 1 or 2 months ago, and that we are going to continue to work on. We have tried to make that the tool is as simple as possible to use for a non-cryptographer, and notably for data scientists. So we have tried to be as familiar as possible to these people. For that, we have followed the very classical the very classical packages, the very classical frameworks that the data scientists are using, and notably Torch and scikit-learn. So I will explain you a bit later what are the different machine learning algorithms that we support today, but you will see that they follow really Torch and scikit-learn APIs. So if ever you have used the Torch or scikit-learn, you should be able to use concrete ML very simply. There is just a few more parameters related to the FHE, but you don't need to know anything about crypto. Notably, you don't need to know how TFHE is working, what is AW or that kind of stuff, which is really, really different from the competitive frameworks, where more or less you have to know the crypto, or you even have to have a PhD in crypto to use them. And then, in addition to Torch and scikit-learn, we are adding a bit more support. So in the next version, you will see that we are going to release like 2 or 3 months. In 2 or 3 months, you will see that we also support ONNX, which is a format which is common to all these frameworks. So it's really great to be able to support ONNX. And since we are going to support ONNX, we will also be able to support somehow TensorFlow or Keras, because you can convert TensorFlow to ONNX and then follow the regular path for ONNX. Also, one thing that I would like to mention is that we are not only very close to this to the APIs of these frameworks, but we also reuse those frameworks a lot. So, for example, for the training, we have not implemented our own training. We are just reusing the training of these frameworks. So we are just subclassing the classes of these frameworks. And when there is something different related to the FHE, okay, yes, sure, we have to code something new. But when it's the same thing, and for example, the training, we just call the regular function. And then in terms of available models, so for the moment, machine learning, it has, we needed it like years to create all of this. So it's not possible for us to make everything in FHE in like 3 months. So we are starting, and also FHE has a lot of constraints. So there will be models which will be much more complicated to turn to FHE. But for now, we are already starting to have a lot of interesting models. So in terms of machine learning, you have the classical linear and logistic regressions. You have the generalized linear model, so notably Poisson regression, if you need it. We have something which really works fine with concrete ML, which is the tree-based. tree-based model. So here's the decision tree. And finally, we have the MLP regressor, so the multi-layer perceptron regressor. So that's one thing. On the deep learning side, so more on the torch side, so we are currently supporting some fully connected networks and conventional networks. So I'm going to speak about the, the constraints and the difficulties. And but I say some because of the constraints, it's complicated to, for complicated data sets to have working fully connected networks or convolutional network. And finally, something which also really works fine is the Ansible methods. So the random forest and the XGBoost. You will see, or you will see if you look at the documentation and the code, that we have plenty of examples with them, and it really works fine. Okay, then let's have a look to how it is. So I told you that it was supposed to be very easy for a data scientist. So now we can check if I told the truth. So here it's an example that we have directly from the documentation. And it's about the use of XGBoost for some task. So we start on the left. So you can see that. So more or less we are. So at the beginning, it's exactly what you have if you use a classical XGBoost. So you start by loading the data set. You split into the train and test parts. Then you define your model with XGBoost classifier. But if you look at the import part, you can see that we are not using the classical XGBoost classifier, but we are using the one from concrete ML. But the way to define the model is exactly the same one, except that we need to define a number of bits which is related to quantization. So I'm going to speak about that a bit later. So you define your model, and then you can use a pipeline. So you can use pipelines as you would use classically in your regular frameworks. And then you define parameters for a grid search. So same thing as you would do on your regular frameworks, you can also define grid search. And then you are launching the grid search to find the best parameters. With the regular tools, I told you, the pipeline or the grid search, we are not re-implementing the stuff. We are just reusing the classical tools. Once the grid search is finished, you can select the best parameters, and you call CLF, the classifier, the best instance, and then you apply your pipeline to the X-train and X-test, and then what would you do if ever you were with your classical framework? You would call predict just to know the goodness of fit. Same thing for us. You also have the predict API just to know what is the prediction, but here it's in clear, so it will be pretty fast. And then if ever you want to have the model in FHE, you need to turn this model into FHE, which is done by a function that we call a compile. So actually it compiles the model into another one, which is different but very close. So you compile the model, which is an operation which is quite fast. And then you have your FHE model, so you can predict on it, which is also done by the predict function. But here you have this extra flag execute in FHE, that you want to set to run the model in FHE. So you will see when or if ever you run this locally on your device, it's a long operation. Depending on your model, you will see that FHE computation is very long. I told you that FHE has been looked for years. So now FHE is doable, but it's still a bit slow, depending on your model. So don't worry, the company and other companies are working on it, and notably in few years, thanks to notably to hardware acceleration, we should have results, or that at least that's the goal of the company. We should have results which are very close in terms of execution time to the execution time in clear. So for the moment, when you want to run something, either you wait or you reduce a bit the number of samples that you use for your prediction. And then you can assert that the result in FHE are equal to the result in clear. Sometimes there are some small errors because computation is complicated to do for FHE to do computations which are 100% equivalent, but most of the time it's equivalent, or when there are errors, it's very not often. So as you can see here, really the APIs are very close to what you would have used if you already are using XGBoost or scikit-learn. It's really, really very close. And it was one of the goals for us. Okay, so as you can see, concrete ML, there is no crypto knowledge which is needed. So you've seen in the previous slide that you were able to see what happens without even knowing how it works under the hood, which was really, really our goal for the product. And really, if you know the other competitive product, you will see that it's much more complicated. It's very, very complicated to do this, because under the hood, FHE is complicated. So for us, we've tried to do this stuff for the users and put that below an API that they know, and not ask them to do this complicated stuff. Another point which is very important for us is that it's open source. I'm going to give the links at the end of the presentation, but it's very important for us and for the company. Eventually, all the tools of the company are open source. So you will see that concrete ML, you can see how it works, but you will see also on the GitHub of the company that you have concrete library, which is the main library which deals with FHE entry points that we are using at the end. And so it's also open source. And a bit later in the year, we also are going to open source a compiler, if ever you want to see how it works under the hood. I'm going to speak about it a bit later, but really something which is very important for concrete ML is that we need to quantize everything. So we have a quantization which is called post-training quantization, so which is done after the training is done. And we also are working on yet another one, which is called the quantization-aware training, in which case the quantization is done at the training time, which makes several things more complicated, but at the same time gives better results, since during the training, you know that you are going to be quantized. So you are going to fit such that the quantization at the end will work better. Our stuff is, so we are using quantization notably because everything in our model will be on integers. I'm going to speak about it a bit later, but everything is on integers doing the inference. And for these integers, we need to have a limit, which is currently at 8 bits. So it's the current precision. In next month, the concrete library is going to extend this limit to higher, and then we'll be able to use it in concrete ML. But for now, when you prepare your model, doing for example, the quantization we're training, or with a post-training quantization, you need to have a model where the integers are smaller than 8 bits. And it has plenty of applications. So each time there are data that you want to protect, you could use our stuff, which more or less, I mean, certainly most of the time you want to protect your data. So for example, for health, if ever you want to, I don't know, detect some disease, but without giving your personal data and without revealing to the machine learning server if ever you have a disease or not. So they will just take your data, I don't know, your X-ray, for example. They will compute stuff to know if you have this cancer, but they will not know if ever you have it. And then they will send you back the encrypted result, and just you, locally on your device, you can decrypt and see if ever you're sick. There are also applications on finance. When they try to forecast the price of this or this stock. Also, for example, for spam detection, and we even have an example in our repo. So, for example, you could detect spams by sending your mails, but encrypted. Imagine that you have a Gmail, but instead of sending them your mail in clear, you just send them the encrypted value of your email. They can detect for you if ever it's spam, and they send you the encrypted bit if it is a spam or not. But they never have access to your mail in clear or other personal data. So yes, I told you that there are some complicated research points in our team. So I'm going to say a few words about it, but it will be, I can't extend it as much as I would want. So the main point, let's say, of difficulty for us is that everything must be on 8 bits. I told you it's because of the limits of the concrete library. So we have to follow these constraints. And so it's when you have something like that, and when you are a machine learning person, you immediately think about quantization, which is the right tool for it. But if you look at the publication in quantization or the available tools, you will see that they have constraints which are a bit different, because they quantize a lot of values, but they have much less limits on the accumulator. So just to explain a bit more what it means. So it means that when you compute your dense layer, so for example your matrix multiplication, you end up with something like y, which is equal to the sum of some weights wi times xi, which is the input. And when you quantize this, it means that you are going to take integer values for wi, xy. So when in the public literature, let's say, when they quantize to 8 bits, it means that wi is on 8 bits, that xi is on 8 bits. And of course, when you add the product of lot of wi, xi, you are going to end up with a Y which can be very large, like 16 or 32 bits, for example. For us, it's not possible to have that. For us, anything in the network needs to be on 8-bit. And notably, the Y, it's going to be used in the next layer for the activation, which is done as the activation is not linear. It's done for, in our case, by a PBS, by a programmable bootstrapping. So really, the Y needs to be on 8 bits, which means that at the end, we need to have weights and integers which are much smaller than 8 bits. So for example, we are going to take weights which are on 2 or 3 bits, and same thing for the XI. And still, it's still complicated to deal with the stuff if ever you have a lot of neurons. So if the sum is on a lot of i's, it's complicated. So what we need to do is to also do a lot of pruning, which is, most of our weights are going to be zeros, such that we can be certain that the Y is only on 8 bits. So really, it's the most painful part for us. And when you are going to use the product, you are going to see that it can also be complicated for you. If ever you try to do deep learning on complicated data sets, very early, you will get accumulators which are too large. And then when you will try to compile them, the tool will tell you that the accumulator is too large and that you need to change a bit your model. So just to explain you a bit, when we have designed the concrete AIML, actually 1 year ago, let's say, we had another approach, and same thing. So things were done for you, everything. But then when you had a problem like this one, the tool was just not working. Sorry. The tool was just not working, and you had no way as a data scientist to fix it. Now we have separated the tool in, let's say, 2 parts. So the part which is related to the crypto, and here everything is done for you, and the part which is related to the machine learning, which is a part that you can, as a data scientist, you can work on. So now when you will have issues because the accumulator is too large, okay, yes, you will have an issue, but it's an issue related to machine learning. And as a machine learning person, you can still try to modify a bit your model, maybe change the way the training is done, or adding more pruning or things like that to fix the problem. So yes, this is the main problem. And so currently with the available daily release, we have a post-training quantization only. So you will see that you have to deal it with limited possibilities. In the next release, we are also going to add the quantization aware training, or a beta version of it, which will be a way. So the training will know that there are these hard constraints, and so it will try to find solution which directly fits these constraints. So you will see that the result with quantization aware training will be much better. Okay, so it was one and even our main problem. Then we have the PBS. So the PBS, I told you, it's the way to replace the activation functions or any nonlinear function by the equivalent of table lookup. So there are some research questions about it, because you start from a function which is a continuous function on floats, and you emulate it by a call to a table which operates just on discrete values. So it could modify a little bit the goodness of fit. Also, I told you that it's a very, very painful operation in terms of execution time. So you want to reduce the number of PBS. So maybe when you know, maybe you were used to use models with a lot of activation or nonlinear operations. If you can change your model to use less of these operations without reducing too much the goodness of fit, it will be much better for you because at the end your model will run much faster. So one part of the research is about reducing the PBS, and another part is also about having the PBS which can be done in parallel. So it's possible to compute PBS on independent values. So at the same time, I mean. So if ever you can do that, for example, you've done your matrix multiplication and then you want to apply a ReLU on all of the cells of your tensor, all of this table lookup can be done in parallel. So at the end, if you have virtually a very large number of CPUs to help you, the execution time of all these PBS will be the execution time of a single PBS. And finally, so sometimes you have to deal with operations which are not activation and which are nonlinear. So there is also research about it. So just to give you an example, if you have a max pool, max pool is not linear. So how do you compute the max of A and B in FHE? So actually, it's pretty simple. There is a trick for it. So what you do is you replace max of A and B by A plus the max of B minus A and 0. Why does it work? So if ever A is larger, then B minus A will be negative. So the max of B minus A and 0 will be 0. So Z will be A. And if ever B is positive, B minus A is positive. So max of B minus A and 0 will be B minus A. And so Z will be A plus B minus A, which is B. So it explains why the equation stands. And then once you have the second equation, you can replace it by a table lookup because it's an operation of a single input, B minus A. So at the end, in terms of FHE, what you are going to do to compute the max of A and B is just to do A plus a PBS of B minus A, which is slow, but which is working fine. So here you have the max of two values, and then if ever you want to do a max pool on a larger kernel, you just apply this recursively to have the max on the full kernel. So yes, of course, it's going to be very slow. So if ever you want to use a network in FHE, what you are going to do is to try to avoid to use the max pool, maybe by replacing by some average pool, for example, which is linear. Or at least you are going to try to reduce the size of your kernel. So instead of having a kernel which is, I don't know, 5 times 5, which is going to cost you about 25 PBS, you might want to use a kernel which is 3 by 3, which is going to cost you like 9 PBS. Okay, so it's the end of my talk, but just to give you some links to what we are doing. So you have the GitHub. I told you it's very important for us to be open source. So if ever you want to see how it works under the hood, if ever you want to contribute, if ever you want to whatever, please go on our GitHub, and please star also. It's important for us to have a repo with stars. So if you have time just to do it for us, it would be awesome. We are also working hard to have tools which are very easy to use, and also so it means that we are spending time on the documentation. If ever you want to use it, have a look to the documentation. There is a lot of explanation and about how to use it, but also about how it works under the hood if ever you want to go further. We also have a Discord. So actually, so we have started to discuss with Cameron thanks to this Discord. So actually, the Discord is not only for Zama or for concrete-ML, it's for FHE.org community, which is which regroups a lot of tools, including competitive tools. And here there are some discussion about FHE, about the user can ask or how to use this, or ask questions about how it works. They can discuss with the maintainers of the tools if they need to have them for questions, or they can explain their application of FHE. So it's very interesting if ever you are interested by privacy preserving tools. And also we have a community if ever you want to ask us questions. So you just ask your questions. There is no dummy question, and we are very happy to answer people who are using our stuff. If ever you want to see also advanced examples, I've shown you an example about the breast cancer, but you have a lot of other examples with decision tree, with including with real life cases. And also, if you are interested, notably by the research side of things, we have some blogs on the Zama webpage about the machine learning. One blog about the quantization of neural networks. So you will see much more precisely how it works under the hood. We also have a blog about how to make quotes of insurance without knowing the data. Okay, that's it for me. Thanks a lot, everyone. If you have questions, I'm here.
Cool. Thanks very much, Benoit. Are you happy to hang around for a few more minutes to take questions?
Yes, I have.
Well, there's already two questions in the chat.
Okay. Yes, let me have a look.
From Cameron.
Is it currently possible to practically train ML model on encrypted information? So yes, it's yes, it's a question that we have a lot. So I'm very happy to answer it. So just to precise, what we are doing in Zama for the moment is about the privacy of inference. So when you want to predict, when you want to predict on encrypted data, but it's not for the moment on training. So for training, there are tools which are much more dedicated, let's say, than FHE. Doing a training in FHE is something that we are going to look at, but for the moment we haven't worked a lot on it, and it's certainly better for you to have a look to other tools like, I'm not a specialist at all, but there is a differential privacy or federated learning, which are tools to make the training without revealing your data. So if ever you need to do training on without revealing the data, it's better to have a look to these tools. Would it be possible to use programmable bootstrapping with encrypted output evaluated using an encoded lookable table? I'm not sure what
to use bootstrapping to evaluate the error signal or loss function is the end of the question.
To evaluate. I'm not sure what you mean. Cameron, can you precise?
I guess because the loss function is nonlinear, like might be a log.
Oh yeah, so actually we can replace any function which is nonlinear and which is univariate, so which is a function of a single variable by a programmable bootstrapping. It's always possible. But it needs to be univariate. So for example, when it's a function of two variables, and when there is most of the time it's not possible to replace by a PBS. There are some exceptions. For example, the max of A and B I've shown you. If you look roughly at it, it looks like it's a variable of there are two variables, so it's not possible. But there are some tricks to turn it into a univariate function, so it's doable in the case of max of A and B. In the case of other functions, you have to see if there is equivalent tricks like that. Okay, and also you will have to see if ever this things are precise enough. I told you that we are replacing stuff by integers, and that there is this limit of 8 bits. So you have to check that with these 8 bits, it's sufficient to get to convey all the information you want. Okay. In terms of quantization limit, yes, 8 bits. Is it likely that the limit will be expanded? Yes. So yes, it's likely because it's really, really important for us. Actually, it's not concrete-ML which has this limit. I haven't told you, but concrete-ML is based on concrete NumPy, which is another stuff by the company to turn your NumPy program into FHE. Concrete NumPy is built on top of concrete compiler, which more or less takes any MLIR program and turn it into FHE. And concrete compiler is based on the concrete library, which is, I told you, the main block, the entry point for FHE. So the 8-bit limits comes from the concrete library. So they are working hard to have more bits. Already they have been able to add bits because 3 months ago it was 7 bits, now it's 8 bits. And they are going to work either to have more bits natively, let's say. So the 8 bits might be 9 or 10 natively. And then they are going to have, let's say, constructions to emulate much larger integers from the native integers. So more or less you split your, I don't know, 32 bits into blocks of 8 bits, let's say, and they are able to emulate the addition of this or the table lookup of this on this emulated integers. So yes, they are going to have more precision, but certainly it's going to be slower. So there is this goal in the company to have more precision, but also to be faster. So thanks either to the software. So we are improving the software, but we are also working on GPUs accelerations, and also, but it's for a bit later, on hardware acceleration. So we have people working here on FPGAs or other hardwares to make that in a few years. So for the moment in Zama, we said 2025, things should be relatively equivalent in terms of execution time to things in clear. But really for that, we will need to have hardware acceleration. Okay.
Jack, I've got a quick question. I enjoyed your presentation. It's a quick question. A lot of people talk about at the moment with standard encryption, the susceptibility of it to be hacked by, or not hacked, but for quantum computing to actually kind of like solve regular encryption. How susceptible is this type of encryption to sort of that type of, how susceptible is it to quantum? So is it protectable, or does it have the same issues as other types?
The LWE problem is secure against quantum computers.
Okay.
So yes.
So even if you had like a fast quantum computer come out, this would be still protected.
Yes.
Okay.
Yes. I'm not a specialist, but it's yes. The LWE is yes.
Is that because it's not a private key, public key encryption? It's because it's a different type of encryption.
Actually, I'm sorry, I'm not a specialist, but from what I know, as the classical, let's say, cryptography like RSA, or if you know RSA or DSA, are based on problems, mathematical problems, which is not LWE, but which is, for example, factorization of integers or discrete logarithm. And it is known that there are quantum algorithms to break these problems in much faster than regular computers. So any problem any crypto scheme which is based on factorization, which is based on RSA problem, which is based on discrete log problem, is going to be broke by a quantum computer. LWE, it's a pretty new problem. So there was not a lot of research about it, like 10 or 20 years of research. For the moment, they don't know any algorithm to break it with quantum computers. So for now, it should be fine. But yeah.
And then my other question is, I think Cameron asked at the beginning, but you're saying, oh, it's better to do federated learning than to use this for training. Is it?
Yes,
but it seems like there'd be some benefit, right? Because like the nice thing about this is that with federated learning, you've got to have like the data provider still has to hold the data and run the algorithms. But with this, you'd be able to just encrypt it and pass it off to someone. So is there an appetite for any application where you would use this for training?
So yes, we would like to work on it, but so for the moment we are very small, so we are focused on something. And also there are some technical difficulties just for the training. I've not gone into the details, but there is something which is complicated in FHE, which is the multiplication of encrypted values together. It's possible to multiply a value by a clear value, but when you have encrypted values, multiplying them is complicated. It's doable, but it's very slow because it's done with a PBS. And in trainings, if ever you wanted to do trainings in FHE, you would have to do this multiplication, which would be much slower. So yes, there is an appetite. Yes, we are working on it, and we have some prototype, not of let's say any training, but for some special kind of models, we might be able to show that it's possible to train them in FHE. But for something as general as a torch, for example, we are very far from it. And it's really not the main concern of the company for now.
Okay, great. Thank you.
Thank you. What is the current time cost for a PBS operation? So it would be better to ask directly the team who is responsible of Concrete Library. So if you want to ask them on the Discord, it's better, Cameron. I don't know because it changed very often. It's very related to the hardware, to the machine you are on. I mean, of course, depending on your computer, it might be different. It's also related to the RAM that you have, because yes, it's not the time of a PBS. Because the important thing is that you can run a lot of PBS at the same time if they are independent. So if your model is sufficiently done such that you will do a lot of PBS at the same time. But yes, for the timings, it's better to ask a Concrete Library. I don't know if there are other questions.
Yeah, does anyone else in the audience have a question? Otherwise, we've already gone over, so I reckon we might wrap it up. Last chance. Okay. Well, thank you so much, Benoit, for coming and giving a presentation. And yeah, we hope to talk to you soon, maybe in person one day.
Yes, I would love to be invited. I hope that I've done such a good talk that you want to invite me. I love your country, so I've said this to Jack a bit before, so I would really love to come back. So thanks a lot for the presentation. Thanks a lot, Cameron, for the invitation. And I wish we will discuss together when you use the product.
Thanks.
Okay, thank you.
Bye-bye.
Bye.